Okay, this tutorial is on naming ionic compounds and naming covalent compounds. So first we'll go with the theory, like why it's so important to naming compounds. So suppose you have this problem where you have sodium. This is a precipitation reaction. So suppose you have sodium phosphate reacting with copper 2 nitrate. This is what's called a precipitation reaction, where both of your starting ingredients are soluble, so they would both be in ion form, PO4 3 minus, and then that 2 right there, which we'll be covering in this tutorial, means that your copper has a 2 plus charge, and then nitrate is NO3 minus 1. And then so you write your, you crisscross your charges, and then you write your formulas. So this is reacting with, this would be aqueous, and it's reacting with this. Aqueous means dissolved. That 2 means you have 2 of these, and anytime you have more than one polyatomic, you need parentheses is aqueous. The 2 will switch, so this will combine with this, and then this one combines with this one, and that's how you get your products. So you're going to get copper phosphate, which just happens to be a solid, and plus sodium nitrate, which is also soluble. So here's the problem. If you didn't know these charges, then you wouldn't know these subscripts, and then you wouldn't know the quantities of atoms involved in this process. And then lastly, you wouldn't know how to balance this. So on this side, if you get all these numbers right, the charges correctly, and this all stems from the names, a little bit of memorization for this one and this one. But all this goes back to knowing the charges that they make, which tells you the quantities of ions they make when they form compounds, and then you could balance it properly, and then balancing it properly will lead you to the right answer if you have a question like this. If you have 5 liters of 0.2 molar of this reacts with 2 liters of 0.1 molar of this. So if you get these, if these are incorrect, you're going to have the wrong balancing, and then you'll have the wrong mole to mole ratios when you try to answer this problem. So actually, I never even made a problem. But what if I wrote how much product forms, how much solid product forms in grams? So you're going to at some point need to compare the mole ratios, so the balanced numbers of all these ingredients. At some point to answer this question, you're going to need to do that. It all goes back to writing the formulas correctly. So if you go ahead and balance this, you would need a 2 here to balance the nitrate, because there's 2 on this side. You would need a 3 here. Actually, because of that copper, now you have 6 nitrates, so you need to change this number, put a 6 there. And now you have 6 sodiums because of that 6, so you'd put a 2 there, and then it's balanced. That 2 also fixes the phosphate, and then it would be balanced. So these numbers, again, they're not possible. It all, like the seed for all of this, for answering this, all started with going from names to formulas and getting the formulas correct. So that's kind of like in the future, we're gonna be able hopefully to answer questions like this. So to get there, we need to cover how to name. Okay, so one of the first things is to on your periodic table, if you don't already, is the main group elements. So main group is that what's called the S column and the P column, and which basically excludes the transition metals. Is go ahead and above each column, like right here, here, 1 through 8, go ahead and put these charges. And X is generic for any element. So any element in that column or family. So all of column 2, for example, or column 2A, it makes a 2 plus charge when they make ions. So column 3 makes a 3 plus. Typically, you pretty much only see aluminum in ionic compounds. And that covers the cations. 5, 6, and 7 make anions. So column 5 makes a 3 minus. So nitrogen usually makes a 3 minus. Phosphorus usually makes a 3 minus. Column 6 make 2 minuses. In column 7, the halogens make a -1. And we usually don't write the number 1. We just write like fluoride ion, chloride ion, bromide ion, etc. Okay, so go ahead and just pause the video, and if you don't have these on your periodic table, then add them above each column. So that's going, if we go back to this one here, for main group elements, that's how we know that sodium makes a +1. It's in the first column. Other rules predict the other ions we see here, but that's like step 1, is knowing this. Okay, so what is an ionic bond? It's typically a metal. So these are all metals on the periodic table, bonded with a nonmetal. So nonmetals, they like to gain electrons. These are all nonmetals. And metals typically like to gain electrons. Oh, I'm sorry, I just messed that up. So metals typically lose electrons. That's why they have a plus charge, because they have excess protons. And then the nonmetals like to get these electrons from metals. They happen to be closer to their octets, and so they like to try to fill their octets by gaining a couple extra electrons. This has 5 valence electrons, 6 and 7, so they're real close to getting 8. These, on the other hand, are closer to when they lose these electrons on their next shell, then they have a full set of 8 on their previous shell. So ionic bonds form between metals and nonmetals. So if we look at a full picture of a periodic table, really bad picture, but all of these, if you see this staircase on your periodic table, these are the nonmetals, and they typically make minuses, and these are the metals, including transition. So you won't see, like, you'll never see iron making a minus charge. So these all make positive. These all make cations, and these all make anions. So we're going to cover in this video ionic bonding and covalent bonding naming. So with ionic, it's a metal and a nonmetal. And you just name the 2 ions. If you have more than one nonmetal, so a nonmetal bonded to a nonmetal, for example, carbon dioxide, most organic things, like things that are like living or once were living, like carbon-based molecules, are typically nonmetals. These come together to make covalent bonds. It has a different naming scheme. So we use prefixes to indicate the subscripts. So this would be called carbon and then dioxide because there's two oxygens. On ionic bonding, we do not use prefixes. You just name the two ions. So that's one important side note about naming. So the next couple slides are going to be covering strictly ionic bonding, and then on the last slide will be covalent bonding. And somewhere in the middle we'll cover acids, how to name acids. Okay, transition metals. So they can have more than one. So on my couple slides ago we went over main group elements. So what about transition metals? They can have more than one charge, so you have to specify with Roman numerals in the name. And then you write that charge in parentheses, and the Roman numerals in parentheses after the name. So for example, copper can be either a 2+ or a 3+. And so if we have this compound, copper and 2 chloride ions, it means that that 2, it came from the charge on copper, so it means that copper was a 2+, and chloride is always a 1-. So if you have copper 3 chloride, that means you have 3 chlorides. That 3 is indicating that copper had a 3+ charge on it, so it would be copper 3+. And then the chloride is always the same. So we'll go over some examples tomorrow in class too that has more transition metals to look at. A couple special notes about transition metals. The following 3 do not have Roman numerals. Cadmium. So in this previous slide I said that they can have more than one. There are a couple transition metals that they only have one, so you do not need the Roman numeral to specify. So for example, cadmium is always a 2+. So if you have like cadmium chloride, it would be that. You wouldn't have to specify. You wouldn't have to write cadmium 2 chloride because cadmium always only makes a 2+. So you don't need that part. Not necessary. Okay, similar with zinc, it's always a 2+, and silver is always a 1+. Something that we use a lot this year is silver nitrate, which is AgNO3. And if you had to write out the name, you would write silver, and you do not need a 1 to indicate the 1+. So you would just write silver nitrate. These 3, they come up often enough to where you should know this. These are the ones that don't need Roman numerals. I think there's a couple others, but these ones are the most common. Another special note is beware of reduced subscripts. So for example, here's kind of like a tricky one that got reduced. So this 2 here, it means that manganese actually had a 4+, and your oxygen is always a 2-. So if you the only other option for this is to write it like this, to say that this was a 2+ and oxygen's a 1-. But we know this is in 6A, and 6A doesn't make a 1-. It's always a 2-. So this is a 2-, and just by reasoning, logic, it must mean that this was a 4+. So when you crisscross this, you would get Mn, just working backwards from this one, you get Mn2O4, which is reduced to that 2 and the 4 can be reduced to 1 and 2. So it would be Mn1O2. So it's kind of tricky, but if you work backwards and you realize that oxygen is not a -1, it's always a -2, you can catch something like that. That's really detailed. It may not ever come up, but just in case it does. Okay, so a couple other notes about, if you noticed, on the polyatomic ions, there's ites and then there's ates. So on sulfite, if you noticed on that list of polyatomic ions, the ones that have ite typically have 1 less oxygen. Okay, and if it has 8, it usually has 1 more than the ite version. Okay, and then the charges are the same. So this is just a way to, if you kind of notice that, you can see a pattern, and it sort of helps with the memorization, or I find. So just one little note about when you have nitrate and nitrite, and sulfite versus sulfate. So, okay, so naming acids. There's a couple rules for naming acids. If you have, it depends on the anion of your acid. So acids can be halogen, or they could be polyatomic ions. So if your acid is a halogen, so for example, if the anion is one of these in column 7, so for example, if you have like HF, HCl, acids typically have a hydrogen on the front if it's a Bronsted-Lowry acid, or HI. Okay, so if you have one of those, this is the way to name it. So you have to use the prefix hydro, and then the base of the element, the halogen, and then you add the suffix ic when you name it. So for example, HCl would be hydro, and this is chlorine, but you drop the ene part and you add ic. So you drop this part and you add the suffix ic. So this would be hydrochloric acid. You have the L. Yeah, hydrochloric acid. Okay, if you have HBr, it would be called hydro, and this is bromine, or the ion is actually bromide. So you drop the ide part and you add ic. So this would be hydrobrome, and then the suffix ic, and then you add acid to complete the name. There's two rules if the acids is a polyatomic anion. Okay, so if it ends in 8, you name it. You do not use hydro. So for example, if you have H, so if you put an H on the front, so hydrogen always makes a +1. So if you have H plus and SO4 2 minus, this, if you crisscross that, you would have H2SO4. Okay, and the way to name that is you don't use the prefix hydro. That's only for halogens. Okay, so no hydro. And you use the name of the polyatomic ion. So it would be this example would actually be called sulfuric acid. Another example, if you had HNO3, this ion is nitrate. So we drop the 8 and we add ic. So this would be called, HNO3 would be called nitric acid. Okay, and I'll do one more using this one. So if you have this, for example, HCH3COO, this ion is acetate. So drop the 8 and add ic. So this would be called acetic acid. Okay. Now, if your polyatomic ion ends in ite, then you don't use ic. So you use us, OUS. So you use that as your suffix. So for example, if you have H2SO3, this would be called sol. So this is the ion sulfite, so it would be called sulfurous acid. Okay, if you have, this should be NO2 here. So if you have HNO2, this ion is nitrite. So this would be called nitrous acid. So a couple examples on acids. Okay, so I have another slide on naming. On if you see these, so these are really common. These are the most common. These are called like these oxyhalide polyatomic ions. So if you have notice the number of oxygens is increasing by 1, so it goes 1, 2, 3 and 4. So look, notice how the name changes. So it'd be hypo if there's only one, and then ite. This one, if there's one more oxygen, there's no hypo on the front here, so it's just called chlorite. When you get to 3 oxygens, it goes from ite to 8, and then when you get to 4, you have 8, and you add the prefix per, so it'll be perchlorate. You could do this with any of the oxyhalogen anions. So for example, if you have BRO minus 1, so you could do this in the same column. You could make this analogous to this, okay, and use this kind of pattern here. So to name this one, it would be called hypobromite. Okay, BRO2, I would like you guys to try that one. BRO3 is now you go from ite to 8 at this point, so this would be called the bromate ion. And if you have BRO4 minus, this would be called perbromate. So sometimes you can name stuff that you've never even seen before just based on what you have seen, and use the pattern. Okay, and use, what would the ion be for arsenate? So if you look at arsenate, arsenic is in the same column as phosphate, and phosphate is this. So sometimes you can name and write formulas for stuff that you've never seen just by seeing something similar that's in the same column. So see if you could write the ion here for this one. Okay, and then I'll check those for work tomorrow in class. Okay, so here's a couple practice questions. So your task here is to try to complete the missing information in this chart. So for I could do one of these just to give you an example. So for number 1, you're given the formula but not the ions or the name. So we have to fill in this missing information. And the ions would be, there's one BRO minus 1. If there were more than one hydrogen, there would be a number here. So there's only one of those two. So that means, since there's only one here and one here, that means BRO has a minus 1. It's kind of like reverse crisscrossing. So this one here is because hypobromite has a 1 minus. And that 1 there is because hydrogen is a plus 1. Okay, and then this would be called hypobromite. Okay, see if you could name 2, 3, 4, and 5. You could pause it, write it down, then I'm moving on to the next slide.